What do an ancient Greek philosopher and a 19th century Quaker have anything in common with Nobel Prize-winning scientists? Although they are separated over 2,400 years of history, each of them contributed to answering the eternal question, what's stuff made of? It was around 440 BCE that Democritus first proposed that everything in the world was made up of tiny particles surrounded by empty space, and he even speculated that they vary in size and shape, depending on the substance they compose. He called these particles atoms, Greek for indivisible.
Here am I to tell you that everything is made of tiny particles, which may vary in size and shape, depending on the substance, and it is composed of, and I call it atoms.
His ideas were opposed by the more popular philosopher of his day. Aristotle, for instance, disagreed completely.
Objection! I believe that matter is made of 4 elements, which is earth, wind, water, and fire.
Stating instead that matter was made of 4 elements, earth, wind, water, and fire. And most later scientists followed suit. Atoms would remain all but forgotten until 1808, when a Quaker teacher named John Dalton sought to challenge Aristotelian theory, whereas Democritus' atomism had been purely theoretical. Dalton showed that common substance always broke down into the same elements, in the same proportions. He concluded that the very various compounds were combinations of atoms of different elements, each of a particular size and mass, that could neither be created nor destroyed. Though he received many honors for his work, as a Quaker, Dalton lived modestly until the end of his days. Atomic theory was now accepted by the scientific community, but the next major advancement would not come until nearly a century later, with the physicist G.G. Thomson's 1897 discovery of the electron, in what we might call the chocolate chip cookie model of the atom. He showed the atom as uniformly packed spheres of positive matter, filled with negatively charged electrons. Thomson won a Nobel Prize in 1906 for his electron discovery, but his model of the atom did not stick around long. This was because he happened to have some pretty smart students, including a certain Ernest Rutherford, who would become known as the father of the nuclear age. While studying the effects of X-rays on gases, Rutherford decided to investigate atoms more closely by shooting small, positively charged alpha particles at a sheet of gold foil. Under Thomson's model, the atoms thinly dispersed positive charge would not be enough to deflect the particles in any one place. The effect would have been like a bunch of tennis balls punching through a thin paper screen. But while most of the particles did pass through, some bounced right back, suggesting that foil was more like a thick net with a very large mesh. Rutherford concluded that atoms consisted largely of empty space, with just a few electrons, while most of the mass was concentrated in the center, which he termed the nucleus. The alpha particles passed through the gaps, but bounced back from dense, positively charged nucleus. But the atomic theory was not complete just yet. In 1913, another of Thomson's students by the name of Niels Bohr expanded on Rutherford's nuclear model, drawing on earlier work by Max Planck and Albert Einstein. He stipulated that electrons orbit the nucleus at fixed energies and distance, able to jump from one level to another, but not exist in the space between. Bohr's planetary model took center stage, but soon it encountered some complications. Experiment had shown that rather than simply being discrete particles, Electrons simultaneously behave like waves, not being confined to a particular point in space. And in formulating his famous uncertainty, Werner Heisenberg showed it was impossible to determine both the exact position and speed of electrons as they move around an atom. The idea that electrons cannot be pinpointed but exist within a range of possible locations give rise to the current quantum model of the atom, a fascinating theory with a whole new set of complexities. Even though our understanding of atoms keeps changing, the basic fact of atoms remains, whose implications have yet to be fully grasped. So let's celebrate the triumph of atomic theory with some fireworks. As electrons circling an atom shift between energy levels, they absorb or release energy in the form of specific wavelets of light, resulting in all marvelous colors we see. And we can imagine Demokritos satisfied that over 2 millennia later, he turned out to have been right all along.